Blockchain sharding. This is the class of blockchain solutions, scaling solutions that I like the most. So that's why I've done the most work on it out of all those scaling solutions that I've done research on. By the way, in case you don't know who I am, I'm a researcher. Mostly I work for the Ethereum project. So let's get started. Basically, the basics of sharding is that in a non-sharded blockchain, every node processes every transaction and holds the entire state. Whereas in a sharding solution, nodes will process a subset of the transactions and hold a subset of the state. And the state here, we mean like unspent transaction outputs, right? And basically, instead of everyone redundantly doing the same work, we're going to try to like share the load, but still have some economic assurance that everyone else is doing a good job, even though we're not actually validating every transaction. So it is a bit complicated. I'm going to give you a high-level overview of this type of protocol without filling in all the details, because the details would take too long. But basically, we can get orders of magnitude more transactions per second if not everyone is doing everything. That should be pretty intuitive. And the nice thing is that we have a very similar trust model to the blockchain-based, like authentication from the Genesis block using proof of work. We don't have like trust models that are based on the nature of the transaction. It's all just proof of work from the Genesis block. So again, more orders of magnitude, more transactions per second, same trust model. So there's a pretty clear appeal there, I think. So there's basically challenges to sharding the blockchain. One of them is that we need to assign miners to shards so that miners from one shard don't migrate to the other in order to produce invalid blocks over there. And so to do that, we need to sample the mining power. And so that presents a challenge. We need to split the state space into shards. We need to process transactions within and between shards. And then we need to deal with all the different attack vectors that exist in this type of solution where not everyone is checking everything. And so there might be something amiss if a block is in a shard, but it's produced by a majority of Byzantine nodes. So the first thing we need to do is, again, sample the mining power. Basically, we can do it, but it means changing the block header. The key to doing this is non-outsourceable proof of work. Non-outsourceable proof of work basically is proof of work where the private key from the Coinbase has to be on the machine that produced the proof of work. So the easiest way to think about this is if you were required to sign the nonce before in the block header. So then it wouldn't just be that the Coinbase could have a private key that the mining pool had. You actually have to have the private key on your hardware in order to sign the nonce every time you change it. So this represents a change to the block structure and will require, basically, in order to do a smooth transitions, like backwards compatible ASICs that everyone switches to after enough people have these ASICs that are able to sign for non-outsourceable work. And basically, it lets you estimate the mining power of various holders because based on the amount of work that they produce with their Coinbase, you can bound their mining power below. So you know that they don't have less mining power than they claim they do using the proofs of work. And basically, so we have to have a way to estimate these. We can have like this kind of tree chain approach where anyone can mine at different parts of the chain, and people with more hash power will mine at the top of the tree, and less hash power mine at the bottom of the tree, so everyone can get their shares in, and we can get a picture of which Coinbases have how much of the hashing power. And then basically, the amount of hashing power that you can use in this non-outsourceable system will be bounded by this estimate of your hashing power, because that way you can't pretend that you have less hashing power than you do and then bring a huge amount of hashing power online onto a shard in order to overwhelm it. So basically, again, we need to estimate the mining power of all these miners, and then we need to sample them and assign them to shards. So again, this is really important because otherwise, if we have a shard that's secured by 2% of the mining power, any Byzantine 3% could go over there and produce invalid blocks. So we need to securely sample the hash rate and then assign it to the shards. So basically, this might be kind of what it looks like. You go and everyone has their Coinbase and signs their nonce, and we get shares, and we can see basically have an estimate of how much hash power everyone has, and then we can and then switching to like a easier to understand drawing and doing a little bit of fault tolerance analysis. honest, then if you basically split up the pie into lots of little slices and then randomly reorder the slices and sample them, the larger the number of slices you have, the higher the probability that you have of having a majority of correct nodes in any given shard. So just from fault tolerance analysis, if we have enough slices of the pie, we can make more shards. So more slices of pie, we can make more shards securely, in the sense that we have a very, very high probability of a majority of correct nodes being on every shard. And again, that's important because if a majority of Byzantine nodes are on a shard, they'll produce invalid blocks, and then other miners on other shards might not be aware of that right away. So, and then basically we can do like a cumulative binomial distribution to see what the probability is of getting any one shard having more than half Byzantine, and so we can like make sure that we have a very low probability of that when we place the samples of mining power into the shards. And then we need to shard the UTXO space. Luckily in Bitcoin, it's pretty easy to see if two UTXOs, if transactions can be processed in parallel or not. It basically depends on whether or not they spend the same UTXO, at least from a given UTXO state. If they spend the same UTXO, then they need to be, only one of them can get in. If they spend different ones, you can process them concurrently. So basically we're just going to split the UTXO space into like mutually exclusive sets. And basically we're going to insist that transactions that spend inputs from shard I are mined by the miners we place in shard I. So basically there's going to be transactions that they process that from their shard to their shard, and there's going to be transactions they process from their shard to other shards. But they need to only check whether the spending is valid. And then they make the outputs available to other miners, including the proof of work, which will basically serve as an economic proof that the outputs were spent correctly. And basically, the blocks have so basically there's two levels of blocks. There's like the top level blocks that like deals with the estimating of people's mining power and assigning them to shards, and then there's low level blocks that are produced in every shard in order to spend these outputs. And then like everyone will be a light client. Well, on all our shards they're not validating. They'll check the work, but they won't process the transactions. And so basically, and these headers will have the headers of the shards will have like Merkle roots for the UTXO state changes. Ideally, we can talk more about that later. And then basically, they will group together outputs that are going to different shards so that they can pass it to those miners from that shard so that they can update their UTXO set to include these new outputs. So basically, again, we estimate the mining power of Coinbases. We sample the Coinbases to the shards. And we split up the UTXOs. And then we validate the work on the low-level blocks, and we validate the transactions on the blocks that we are assigned to as an individual miner. But this is so on the top level block, it's just SPV of all the low level blocks. And here's a little drawing. So here we have the top level block, and then basically in the transaction, the place where transactions would normally go, we have block headers for the different shards. And those block headers have groups of transactions for the transactions that are from the shard to the same shard, from the shard to the other shards, so that we can basically keep track and pass the outputs around between the shards so that everyone can happily move their outputs around in order to spend them. Additionally, I didn't mention this, but I should have, transaction has to spend inputs from the same shard. That's important because that way there's a particular set of miners that you assign your transaction to. If you're spending inputs from multiple shards, then multiple miners from multiple shards would have to see it. So basically the question is, okay, how much does this actually give us? And hopefully you're kind of convinced that it's secure from a Byzantine fault tolerance analysis point of view. And basically, so we have this top level chain, which in the more overhead we add there, we can add more shards. So the number of shards is linear in the overhead of the top level chain. So basically, so if we assume that like half of a node's processing and bandwidth capacity is going to validating the top level chain, and half is going to processing transactions on the shard. Then linear increase will increase the linear increase in everyone's like computational power. If we increase the block sizes, will lead to a linear increase in the number of shards and a linear increase in the transactions per shard. So that means that basically we have an order of n squared number of transactions, where n is like the number of computational resources that that like the minimum powerful node has. Whereas like now when every node does every transaction, then we get on the order of n, because because every node needs to keep up, and so you're limited by the weakest node. Whereas here you're limited by O of n squared of the weakest node. So this is a significant improvement in the number of transactions per second that we can do. Basically because it becomes superlinear instead of linear in the computational power of any given node. So increasing the block size has a bigger effect in a sharding solution than in a non-sharding solution, because we get this O of n squared instead of this O of n increase. Just to illustrate this, basically, if we increase the computational power, so the beige color represents the overhead for checking the top level chain, and then the different colors represent the overhead for checking the shards. If we increase the amount of computational power, the top level shard can keep track of more. The top level chain can keep track of more shards. So we add another shard, and we get another, a linear increase in the number of transactions per second that we can do because we've added another shard. And also the shards get longer because we've assumed that we would insist that we spend half of the time validating the block header for the top level one, and then half the time processing transactions. So we get this square increase in the number of transactions that we can do when we increase the capacity of any individual node. And then there's basically security problems, as you could imagine. One problem is like people might crawl outputs all into one of the shards because we give them the option to move them because they need to spend them together from a shard. And then basically on every shard you're going to have an independent market for transaction fees. And if people crawl lots of outputs into a shard, then it'll be expensive to spend transactions there. And so you will move outputs out in response to people's corralling transactions in. So that's like the way to deal with that. Invalid blocks is another problem where basically a miner will produce an invalid block in a shard, and then if we don't find out about it, other people will process transactions on outputs from that shard, from that block. And this is especially bad in economic analysis rather than Byzantine fault tolerance analysis, because in economic analysis you can just convince all of the rational nodes in a shard to go with it on the fly after they're sampled. Whereas in fault tolerance analysis, you kind of have to have them be faulty ahead of time before the sampling. And then basically what we can do is there are challenge response protocols that really cleanly deal with this, because if you mine an invalid block and someone challenges you, they can get your block reward if it turns out that you're invalid, that your block was invalid. And if people don't agree as to whether or not it's valid or not, then there's a big incentive for people to find out, download that block, and verify it, because they will gain from this market of where people are betting whether it's invalid or not by betting on the right side. A much harder problem, though, is to deal with unavailable blocks, where you don't know if the block is invalid or not, but you just can't find it. And there are challenge response protocols here where basically you want to show that this data is unavailable, but you can't do that because you can't prove that the data is unavailable. But what you definitely won't do is build a block on top of their block if you can't find it. Because if you build a block on top of an invalid block, that's an invalid block, and then you won't get your block reward. So there are ways to deal with that as well. So basically, this has gone a lot quicker than I thought, I think. But basically, so some of the takeaways are that we can do more transactions per second without changing the trust model. We still will basically count the total work from the Genesis block, only instead of just looking at the header on the top level chain, we'll add up the work from the headers on the shards as well. So it's the same trust model. Okay, the work is non-outsourceable, and we need to do this in order to sample and assign miners to shards. And the protocol is complex, especially once we start talking about these challenge response protocols and the betting to deal with basically what I call escalation. Like what if something goes wrong on one shard? Then we need to have more attention be there. And So it is a bit complex. Another thing that I should mention is that if you find a block to be invalid, then that block needs to be reverted, and so do the blocks that spend outputs that block sent. So there could be a good amount of block reversions as a result of finding one invalid block. So it's very important that we find it and then that we revert the transaction, because it might lead to a reversion of blocks from other shards, not just the shard that you're in. So basically, I'm wondering if sharding is the future of the Bitcoin blockchain. I don't know, and I hope that you guys maybe will have an opinion, and that you'll talk to me about it. Thanks a lot.